Most of the main results involving limits that we're going to be looking at are going to involve fractions, so it might be good to review some of the basics here. You're not likely to be too impressed if I tell you that 6 divided by 3 is equal to 2, but what might be a little bit more interesting is that there are two very distinct ways of interpreting what I just said. When I see a fraction, that is suggestive to me of breaking things into pieces. Here we're taking the 6 and breaking it into 3 equal pieces. Each one would be of size 2. If instead of thinking of 6 over 3 as a fraction, we instead think of it as dividing 3 into 6, then we're using a very different model. We're asking ourselves how many 3's fit inside of 6, and of course 2 of them do. If you think about what you're saying when you're talking about fractions, then you tend to be bouncing back and forth between these two interpretations. The chopping model causes us to think about fractions in a certain way, which can maybe be best explained by showing that a fraction can be written as a product of two different numbers. First can be written as the product of 3 with 1/4. This makes clear that the purpose of the denominator, the 4, is to cut 1 into 4 equal pieces. The numerator, the 3, is just counting how many of those pieces we're going to include in our number. So to repeat, the denominator tells us the size of a piece, and the numerator tells us how many of those pieces we include. So what about 1 divided by 1/4? Rather than citing a memorized rule, just note that the 1/4 is a piece of the whole of a certain size, so that exactly 4 of them fit inside of 1. So the division that we have listed right here should give us an answer of 4. Similarly, 3 divided by 1/4 is 3 times the quantity 1 divided by 1/4. The 1 divided by 1/4 becomes 4, so we get 3 times 4, or 12. The fitting model provides immediate insight as to why dividing by 0 is not going to work. To illustrate, let's start to build a little table. The smaller the number is that we divide by, the bigger the result will be. So when we try to divide by 0, what can possibly come from that? You can fit an infinite number of zeros into 4. Maybe we want to say that 4 divided by 0 is going to be infinity. However, infinity is not really a number. It doesn't do a lot of things that you would want a number to do. Ultimately, we're going to say that dividing 4 by 0 is just meaningless. Another way of saying that is to declare it to be undefined. Just in case you thought we might have been a little bit hasty in dismissing infinity as being meaningless here, let's consider a similar analysis using negative numbers. Things are going to proceed pretty similarly, except because we're dividing by negative numbers, we're going to get negative results. So what is the analog to an infinitely small negative number? Maybe division by -0, but -0 is the same as 0. If we divide by -0, so to speak, the best we could do is to say negative infinity, but that wouldn't agree with what we got before when we were dividing by 0. So let's just leave well enough alone and declare division by 0 to be undefined. Okay, a 0 in the denominator of a fraction is never good. What about a 0 in the numerator? Let's look a little bit more closely at that. Looking at 0 over 4, as before, we can break this up into a product, but 0 times any number is just 0. By the same logic that if you put 0 apples into an empty box, it's still empty. There's nothing in it. So 0 in the numerator of a fraction is no problem at all. And we recall that a 0 in the denominator of a fraction is always going to be a problem. Actually, there's a case that we haven't considered yet. What if we had 0 divided by 0? This gets a bit tricky. Grab yourself a number and call it x. Then x times 1 over x has to be equal to 1. After all, we're asking how many x's fit inside of x, and certainly one of them does. However, the numerator is always supposed to be for counting. And 0 anythings is 0. So which is it? 0? 1? So let's be content to say that 0 over 0 is also undefined.